finish the. Okay, I just want to finish the discussion of this delta symbol method at the beginning of this lecture with something I'll call a non-Abelian challenge. Right. So I want to modify the setting slightly. So I want to start with a finite dimensional associative division algebra over a number field F. I mean, we could also do global fields, global function fields if you wanted. So if you haven't thought about these things, then these things are forms of matrix algebras. So if you go pass up to the algebraic closure, then you're going to get n by n matrices with coefficients in F bar for some n. Sorry about that. And inside of here, you can pick a maximal order. And this is an analog of MNOF, all right? Okay, so instead of a polynomial in this setting, you have a polynomial that is in non-commuting variables. So you can think about it as just being a polynomial in a bunch of matrices. So non-commutative polynomial. All right, and let's let delta be our sort of way of choosing size for this thing. So, and so, for example, if my division algebra splits at infinity, then this is isomorphic to and F infinity, then delta R bigger than 0 goes to delta F infinity, which is isomorphic M and F infinity. And it's just going to send R to R times the identity matrix embedded diagonally. So just make sure that I don't, yeah, I'll say that in a minute. So in this setting, you have as a vector space that D is Fn squared as a vector space over F. dV, which just by definition I'll take to be D tensor over Fv, is isomorphic to Fbn squared, right? And I'll just set D dA F isomorphic to D tensor over F AF, which is isomorphic to A F n squared as an AF module. Right? So with these things in mind, we have a definition for any vector space of Schwartz spaces attached to these local objects and to these global objects. So I can define the Schwartz space dV and the Schwartz space, the adelic Schwartz space, because I know what they are for all, well, free AF, well, anything isomorphic to AF to the n squared, and also for any vector space. I also have Fourier transforms. I'll just write down the adelic one. And it sends F to X maps to integral over d af fy psi of reduced trace of x, y, dy. And the reduced trace is just, think about it as just being the trace. There's also a reduced norm, which you should think about as being just the determinant. All right. Okay. All right. And you have Poisson summation. Poisson summation holds because, after all, I mean, all of this information is just saying something about, it's just saying something about what's going on at the level of a vector space. Okay. So let's go through our circle method study. So if I had f, that f infinity, say, that's an element of the Schwartz space of df infinity, then I could study nx, which is the sum over all c in OD to the n, p of c equals 0 of f infinity c over delta of x. All right. So remember, I mean, this is a non-commutative polynomial. So I mean, you could even have something like xy minus yx equals 0, and you'd get something non-trivial out of this, e.g., right? And instead, you could study, and it's more flexible to study the sum over c in d to the n of f c over delta x, where p of c is equal to 0, right? And f is an adelic Schwartz function. Okay, so this is somewhat more flexible than the first situation. And so the question is, why don't we try, as sort of a new source of circle method type problems, to study these two sorts of sums? So here's some remarks. Dn is, after all, it's a vector space. So the point is to exploit extra structure. So in other words, I mean, if you sort of set yourself up, you may be able to apply the circle method in, you know, the classical sense, because after all, we're cutting out, I mean, if you look at each of the matrix entries, this is some collection of polynomials on a vector space. And you could say, okay, well, I can just apply this to you know, good old-fashioned circle method. The point is utilizing the extra, or using the extra structure, you might try to reduce the number of variables necessary, because this set of polynomials has rich structure. And another question that I have is you know, what can we do about secondary terms in this setting, even for quadratic forms? Secondary terms, sorry. All right, and my thought is that really this is going to have something to do with some sort of Langlands-L functions, and I'll say a little bit more about that in just a second. Okay. So I want to say what the non-abelian delta symbol is in this setting, and you know, now that we know what it is, I mean, you can sort of guess how the proof is going to go, but I'll just highlight a couple things. And this is the last time we'll see this in this lecture series. So here's a proposition. So if I give myself phi, and I mean, we're just copying at this point. After this, I'll stop writing the same proposition over and over again. This is sort of the leitmotif for this. Okay, so I want my standard assumptions. All right, and then for Q that's sufficiently large, we have delta M is equal to CQ E over Q n squared F over Q of sum over D in D times of phi D inverse M over delta Q, delta over Q minus phi of D over delta Q M D inverse over delta Q. Okay, now notice these variables do not commute, so it's important which order I take the D inverse and the M in this, right? And here CQ phi has the same form as before. O n phi q to the negative n, right? And the proof is the same as before. And I'll just say it one more time. I mean, this will be a promise for this thing. So I just do the same trick as before. All right. I note that this is equal to 0 if m equals 0 and sum over d and d times of phi z d over delta q. If m is equal to 0, and this is by a change of variables, d maps to d inverse m.
Jayce, one of those is a not equal to 0.
Not equal to 0. M is equal to 0, so this is m is not equal to 0. Thank you. Okay. All right, and then you use Poisson summation to estimate this term as before. So here's the challenge. It's to use this to prove analogues of the standard applications of the smooth delta symbol. But the point is with non-commuting variables. So as a first step, and this is just a challenge. I don't have any theorems in this. I think but I think it would be fun for somebody to work this out. So as the first step, I just want to make a few comments. So as the first step, of course, you do Poisson summation in D. Okay, and let me just make a comment. This was one thing that makes this interesting. That what's the analog of Mellon inversion in this case? So I'll just remind you that in the other settings, when you apply the Poisson summation formula, then you get some sum, and then you try to understand what it is as a function of these d, which are essentially your moduli. And in the other cases that I know about, these d turn into things that you can estimate by taking a Mellon transform, and they give you some sort of L function. So the fun thing here is that you can still do Mellon inversion But the melanin version is not going to give you something in terms of Hecke characters. It's going to give you sort of something in terms of automorphic forms on D. So the sort of thing that you're going to be using is a formula like the following, that this sum over x and d times can be written as the sum over some orthonormal basis of, well, I'll say what that is in a moment, integral over d a f times fx px norm, reduced norm of x, the s dx ds, where this is over orthonormal basis of L2 d times a, well, maybe r bigger than 0, d a f times. All right, and by the Jacquet-Langlands correspondence, I mean, these are going to, I mean, this is essentially a sum over cusp forms on GLM, where, I mean, rather than go back up, I'll just remind you that this thing, if I pass to the algebraic closure, I get something that's isomorphic to m of f bar. Okay. So I think it'd be fun to look at what, yeah, I mean, so Farrell asks if you're using the assumption of division algebra. Of course, everything would work for mn of f, but the statement of the delta symbol is going to be more nasty. So you sort of have to pick your poison. You either want to end up working with things on a division algebra, or you end up working with a delta symbol where there'll be additional sort of boundary terms in this. I mean, my expectation is that you could do the same thing for a matrix algebra, but then when you try to estimate, you're not going to get such a clean cancellation. There's going to be contribution from things that aren't invertible, and so you're going to have to play with that. But I just think it would be fun to work this out. And my suspicion is that when you compute these L functions that, sorry, when you compute these Mellin transforms, that you're going to get something that looks like some L function of the automorphic form, at least for quadratic forms. It'll give you some L function of the automorphic form sort of up to first order. I don't expect it'll be an honest L function, but it'll sort of, maybe it'll have the same poles as some L function. It's not even an honest L function in the case where m is equal to 1. See. And I think, I mean, there's some hope that you might be able to combine this with some ideas that I'm going to be talking about next, but I think this is something for its own sake. It might be fun to work this out. All right, so I think I'm going to start a fairly different topic at this point. So if there are any quick questions on this before I move on, then now would be a good time.
Yes, can I ask you a quick question?
Yeah.
I thought you mentioned for the application for quadratic forms in the for the original setting.
Yeah.
I thought you said that you don't need the delta function, like the adelic version.
You don't need it if you're only going to work over Q.
Right. Would you expect something similar here, or nothing like that?
I mean, I mean, basically, as a matter of principle and taste, I would think that you probably just want to work in general. But
okay,
if one insists on trying to get it to work over Q, then you could set up the same thing.
Okay.
You'd be looking at some sort of, I mean, the easiest examples would be division algebras, right?
Right.
But I'm sorry, like quaternion algebras over Q. I mean, and then you could pick a maximum order and you could work classically if you wish. But
sure.
I think you will find that if you try to get into it, that you're punishing yourself if you don't adopt language.
Okay.
But I mean, this is it's a matter of taste.
Okay,
So
thank you.
Are there any other questions? So certainly in this thing, the point is not that, okay, works for MD to MN, MD to MN. And one algebra included in the I'm not sure I follow, but maybe we can talk about that later, because it may take too long for me to, just out of my own ignorance. And that's not to say, like, whoever just asked, I don't know who just asked the question about doing things over Q. I mean, doing it over Q would be very interesting too. And if that's helpful to somebody wanting to do this, then I mean, I would encourage them to do that. I just, especially because you're going to start working with, you're going to end up with some automorphic forms here, and it's going to be helpful to adopt this perspective, but it's not necessary. Okay, so I think I'll stop with this and move on to something a little bit different. So this is sort of part 2, and this will probably take up the rest of my lectures. So this is Fourier analysis on Braverman Kazhdan spaces. And I mean, we'll also talk about a few things about more general spherical varieties. All right, so here's section 0. Motivation from the circle method. All right, so, all right, so let's go back to our original sum. So Q of C equals 0. So I'm just taking some quadratic form in an even number of variables. And it has the following form. Okay. So I have a main term plus C2 x f over Q n plus O of n minus 1 plus epsilon. All right, and here f is some Schwartz function on AF2n. Right, and then the question is, what is the meaning of C2? All right, so I want to think about this, and I want to sort of make the argument that C2 is a boundary term. All right, and I'm not going to be very precise about this, but I mean, let me sort of give you some flavor. So let's look at Fn. So Fn contains 2 GLNF orbits, namely 0 and everything that's not 0. Okay, so when we apply Poisson summation, if I give you some test function, I look at C over delta X, C in Fn, then I get one term that is of size. It's just a term that corresponds to the boundary, and then I get a sum over everything else. Okay, and I mean, as we all know, then like, if there's no other, if there's nothing else that's messing with it, the terms that I've written here are not going to contribute as much because they're rapidly decreasing as a function of x, and then this term is the main term. Okay, so the moral of this is that the boundary term gives you the main term, and then the terms that are sort of some open orbit don't contribute as much. And so the question I'd like to ask is that, can we think of C2 as a boundary term? And I mean, just as an answer, I don't know explicitly, but I think it's fairly clear that you can make this precise. But when I say this, I mean, well, boundary term in what, right? So, I mean, we have to have some geometric structure to sort of even get started asking these questions. So let's talk about the geometric structure that's present here. So I'm going to just start by giving myself a non-degenerate quadratic form from, say, Fn to F, non-degenerate quadratic form. And for F algebras R, the phi of R equals that of V and R to the n, such that QV is equal to 0. And this is just, I mean, I have the habit of, when I'm writing down affine schemes, say that I write down their points in some test R algebra. So that's what R is going to mean. So the original sum, and by original I mean the one that we looked at up here, I can just rewrite. So this is up here, it's the sum over all C that are zeros of this quadratic form, and I'm just going to rewrite that as the sum over C and C of F C over delta X. Okay, so now I have a similitude group of this form. So it's the set of G in GL n of R, such that the quadratic form is preserved up to a multiple. Am I doing this correctly? Now I think, let me just say, now that I look at it, I think I'm doing something wrong. So I want G, V, GW to be equal to lambda times G or V, W, where this is the pairing attached to quadratic form. Then GOQ acts on CF with two orbits. So it's CF minus 0 and 0. All right, so we should certainly think of C1, the big constant term that we had up there, as a boundary term attached to 0, right? So my suspicion is that C2 is attached to a quadratic space dimension 1 smaller or dimension 2 smaller. Right. And so I have some preliminary work on this, but I don't really want to talk about that. Right? But one thing that, if you're paying attention to this, you should protest. So these comments were sort of predicated on the assumption that, in the Poisson summation formula, we start out with a vector space. We do Poisson summation, and then we decompose the vector space under orbits of some group, right? But here, I mean, if we're just thinking about things in terms of classical Poisson summation, then I mean, you should protest that, you know, CF doesn't have a notion of, or it, you know, you can't just apply Poisson summation in the usual sense to CF and expect to end back at CF, right? So in order to make this precise, so to make precise, need a notion of Poisson summation for C of F. And this is known. Right? And it's been known in sort of automorphic land in, you know, for some time in some somewhat different form, but in this case, but sort of there's been more attention paid to it recently because of some conjectures of Bremerman and Kazhdan and others that, and Saclarides and Go and Forg and et cetera, that I'm going to talk about now. Okay. So, Poisson summation conjecture. So this is where I'm going to talk about these conjectures. So I'm going to give myself an affine scheme of finite type over F, and I'm going to put assumptions on it later. So I'm going to want it to be normal, for example. Okay, and so if you're, you know, it's funny, there's sort of a question of taste, you know, if this sort of, you're not comfortable with this language, then the following is just fine. So for every F algebra, R of X of R is just the set of C and R to the N, such that some collection of polynomials is 0. Okay, so this is just the 0 locus of some polynomials for PI that are in F X1, X to the N. All right. And now what I'm going to do is I'm going to assume that a group acts on the right. All right, so I'm going to need this to be an algebraic group. And so what this means, I mean, this is supposed to be a course, right? So I'll say precisely what this means. So what I mean is that I have an algebraic group, G, such that for all maps of F algebras R to R prime, I have a little commutative diagram. Okay. And what I mean by this is whenever so if I take the system of equations and I look at a solution with coefficient, a solution in R, then I get a solution in R prime. So I can have maps from the top to the bottom here on this diagram. And the top map and the bottom map are just action maps. These are all just sets. All right. So I'm going to have to put some assumptions on things. So I'm going to need to, for my purposes, I'm going to assume that G is reductive. Okay. And again, since this is a course, I mean, this is if and only if it's unipotent, radical, is trivial, which is, you know, if you don't know what that means already, that's not very helpful. Another sort of more interesting way to say it is that all representations are completely reducible. And probably the best thing to do, if you haven't seen this, is just think G equals GLN or SLN or GOQ or symplectic group, but not something like that's upper triangular, so A and R. All right, so the last is a non-example of a reductive group, and the other, these are all examples of reductive groups. So these are just matrix groups. And you know that for each one of these groups, I know what it means when I take the R valued points. You know, they're matrices with coefficients in R that have determinant that's unit in R, for example, for GLN. Okay, so I need a few more assumptions. So I'm going to need to assume that G acts with open orbit in the Zariski sense. X is normal, so its singularities are not too bad, and satisfies star. Okay, so I'll say what star is in a moment, but I'm not even sure whether this is actually, I mean, the spoiler is I want to say that it's spherical, but I'm not actually sure whether this is necessary for what I'm going to be talking about, although the primary applications seem to be in that case. So here's the conjecture, the Poisson Summation Conjecture. All right, and there's a bunch of names attached to this. So Braverman, Hausdorff sort of first came up with this in a special case around 2000, and Go rediscovered some of it, as did Laford in a slightly different context. And Go refined some things about this and sort of made some things more clear. And then Sacclarides partially generalized it to the setting of spherical varieties. It was in a more restricted setting prior to that. And then I'll just say plus or minus epsilon. So whatever's wrong in here, you can blame me if you wish. All right. So the first assertion is that there exists a Schwartz space that is a subspace of smooth functions, not on the whole space, but just on the smooth locus. So functions in the Schwartz space don't have to be defined on the whole space. And it's important to allow singular things. There's Fourier transforms, fx, such that fx is twisted GAF equivariant. All right, such that the Poisson summation formula holds. If f satisfies certain local conditions. Maybe I'll put a smooth here. So it should be true for any f, but the general formulation is going to have to incorporate some sort of boundary term for which there's not a very good description at the moment. So the type of local assumptions I'm thinking of are, say, for example, you might assume that the Fourier transform vanishes at 0 and then the function vanishes at 0 or something of that nature. And that's the sort of thing morally that you should assume in order to get rid of these boundary terms. Moreover, you should have that this thing breaks up as a restricted direct product. Okay, and when you give a restricted tensor product, and when you give a restricted tensor product, you have to say what your vector is at almost all places, and your vector at almost all places is the so-called basic vector. BXV is an XFV such that FXV of BXV is BXV. All right. So one thing that's sort of remarkable is that in general, BXV is not equal to the characteristic function of XOV, or the characteristic function of the integral points of the smooth locus, right? So the issue is that singularities seem to force this to be false. All right. So, all right. So there's a few comments that I should make about this thing. So, I mean, maybe before I go on, I mean, let me just remind you that what we're sort of positing here is that you have a notion of a short space. It's a subspace of the smooth functions on the smooth locus, a Fourier transform that satisfies some equivariance property, some version of the Poisson summation formula that has not been stated precisely. It's only stated for functions that satisfy certain assumptions. The short space should be a restricted direct product with respect to these basic functions. Okay, so let's do some remarks. So what should we assume about X? All right, so Saclarides suggests X spherical. And certainly from the point of view of automorphic representation theory, this is the most important case. But I don't actually know a theoretical reason why this is necessary. And certainly you can give examples where these sorts of things exist where the space isn't spherical. Right? So as stated, does the Fourier transform hold with Fourier transform? Yeah, but I didn't specify any sort of twisted equivariance, right? So I mean, I'm being vague about I mean, it's difficult in general to say what you should mean by twisted equivariance, but effectively, what you want is you want that, say your group G has one-dimensional center. You're going to want something that essentially flips the sign of the center under the Fourier transform, just like the determinant does. Okay, do we know what the analog of convolution is? Do we know what F inverse FC dot F is supposed to? I think I'm going to hold off on that because it just disappeared. So what the analog of convolution for? Honestly, that's not clear to me at all, what the analog of convolution should be. I mean, in this level of generality, you just have an action of G. You don't necessarily even have a product on the space. So one has to be a bit careful. In fact, I mean, these things are also, the comment that just came up, I mean, this is sometimes called a non-Abelian Poisson summation formula because the spaces aren't vector spaces. So, I mean, when you define convolution, as was just asked, I mean, you're using addition, right? So, right. So, in many cases, when X is spherical, we can compute the space S of X. Let me just call it smooth FV GO FV. All right, let me just call it compactly supported smooth function, for example. Using, I mean, in the cases of reductive monoids, which I'll get to in a minute, this is sort of just the Satake isomorphism, but in general, you can use essentially Saclarides thesis and earlier work than that in many cases. And this allows you to give an ad hoc definition of basic function and xv. And in fact, I mean, maybe ad hoc is not the right word here, because the basic function will be the correct thing. It's just, it is what it is. You'll be able to write down what you want here. The ad hoc thing is giving this Fourier transform. It'll just be the restriction to this subspace C upper infinity X smooth FV GO FV. So you'll sort of know what you want it to do on the basic functions, and then so you can give an ad hoc definition for this space. So in some cases, what this amounts to is just formally writing down the Satake isomorphism. So it's not, I mean, it's perhaps not so enlightening. So Bouthier can go Saclarides and Saclarides-Wang can give a definition of EXV using function sheaf correspondence and perverse sheaves on the arc space. Okay. So there's the idea is that there's sort of a, I mean, there's an elegant way of writing down this basic function in terms of geometric data. And it works in, I mean, this is something that currently works just in equal characteristic, but you know, as Cho said once, if you say perfectoid a bunch of times, you can probably get it to work in the other case. Or maybe tilt and tilt. But this is a definition of the basic function. I mean, you can prove that it gives the same answer as the, you know, as the basic function that you sort of get via more elementary means. Another thing that is kind of fun is that XFV should be local. I didn't understand why this was important for the longest time. So there's a sheaf theoretic way of saying this, but the thing that sort of, which as far as I know, for example, doesn't make sense in the Archimedean setting, but there's a more down-to-earth way of saying this, which I think Joe tried to explain to me once, but I didn't understand it for a long time. If you just view your X as living inside some GAM, then your space SXFV should be preserved by multiplication by restrictions of functions in S f v to the n. Okay, so one way of interpreting this is that somehow the short space should only depend on the neighborhood, sort of the germs of functions in the neighborhood of some singularity. If you hit them by a Schwartz function, sort of smooth them out, and use that to cut out a neighborhood if you want of some singularity, you should preserve the short space. Okay, right. So, I mean, okay, so this is some conjecture. So, you know, why do I care? Well, this implies Langland's functoriality in great generality. And the idea is that you can mimic the Godemont-Jacquet method of producing L functions and use converse theory. I don't think this is really the venue that I want to talk to go into an in-depth discussion of this, but just if you're not familiar with this, Godemont and Jacquet's method is based on Tate's method, which is based on Hecke's. And the idea is that, and Hecke's is based on Riemann's, and you know, everybody in science already knows how to prove the functional equation for the Riemann zeta function. It's essentially equivalent to Poisson summation. Okay, so you just amp that up several levels, and you get to Godemont and Jacquet. And the point is that this, you know, what underpins all those methods is this notion of Poisson summation, and in some sense, it's equivalent to it. Okay. So, yeah, I think I have some time to do. So, William kindly suggested that I give some examples yesterday, and I think this is maybe a good time to do it. I don't know how far I'll get with this, but I mean, what I don't get, I'll get to next time. So, a fun class of examples, which is really where the theory started. And this is what this is all. This is this case that Bremerman and Kazhdan studied and Go studied, and something related is what Laurent Lefort studied. And so, what are reductive monoids? It's the analog of taking GLN and putting it inside n-by-n matrices for a general reductive group. So, in order to sort of give some information about what's going on here, and if you're not familiar with this, it's probably not. I mean, we'll go back to something that's a little bit more analytic in a moment, but I'll let G hat be the complex dual group of my group G. So this is something over C. And if you don't know what this is, then I'll just write down what it is in the classical cases. Hopefully I got the things right. So you just take the root datum and you flip it, if you know what that means. All right. So if I'm given my reductive group split over F, and if you don't know what that means, all the cases that I wrote up are split, so you could take any one of those, and a cuspidal automorphic representation pi of GAF, and a representation of this hat thing, then you obtain a Langland's L function, L of S I rho. Okay. So one of the things that Bremerman and Kazhdan sort of succeeded in doing is figuring out what the right geometric space you should look at for this rho is. All right. So the space you should look at is M rho, which is the reductive monoid attached to rho. All right. Now there's some assumptions that you have to make on G in order for what I'm about to say make it valid, but I sort of want to suppress those. So here's some examples. So for our good old symmetric power L functions, right? So here pi is just on GL2. And I'm lying a little bit here because to make this theory work, you may want to view it as being on SL2 cross GM in some cases, but I don't want to get into that. My symmetric power L function is takes me from here to GLK plus 1 C. Then in this case, my reductive monoid is Mn in M2R, 2 by 2 matrices cross R, such that the determinant of M is equal to n to the k. So the most natural thing in the world. Okay. Right. So another of my favorite example is the triple product L function, which is the following. Sorry, let me change the notation a bit here. So this is like a three-dimensional or three-copy Rankin-Selberg, if you've heard Rankin-Selberg L function before, where the pi I are on GLRI, and tensor cubed is GLR1C cross GLR2, GLR3C, mapping to GLR1, R2, R3C. And in this case, your reductive monoid is just going to be sort of what you think it should be. It's M1, M2, M3 in MR1R cross M2, R2, R cross MR3, R, such that their determinants are all equal. Okay. So just as a comment, I think this is a good place to end for today. If you have the Poisson summation conjecture for any of these things, then you certainly are going to get secondary terms in these counting functions nx. And they're going to correspond to sort of poles of L functions that occur in this thing. And in fact, I've just been thinking about Cuss forms, but there'll be some sort of filtration of the poles. And secondary, I mean, you're also going to get tertiary terms, etc. And one question is, can you obtain nx independently? All right, so can you obtain these secondary terms? Right, and the interest, of course, is that this would give you conversely information about the poles of L functions. And so it's not clear in general. But in one case, I worked this out as an application of the work on quadratic forms that I mentioned earlier in this lecture series. So this is an AJM. So this works if I look at the reductive monoid that's attached to the Rankin-Selberg product of two representations on GL2. So where det M1 equals det M2. So in this case, NX is counting, I mean, in the case of, say, this M row, you're counting points M1, M2, M3, such that these three determinants are equal. Okay. And just so I don't have to worry about the normalizations, let's just say that R1 equals R2 equals R3, and then you want them all to be the same size. In general, I'd have to think about the normalization that you want to get something with the Poisson function. Okay, but this is a perfect place to stop. So for